we're going to continue what we were doing yesterday, and I actually I'm going to continue a little bit of that video. So let's get started here. Last time there was one equation that we were finding the volume of. So now we're going to move on.
Unfortunately, this technique does get a little trickier. While rotating one function around an axis gives us one type of solid, if we take the area enclosed between two functions and...
Okay, so you see here you've got two functions. You've got the blue one, and then you've got the red one, all right? So what we're going to do now is it's that yellow area, that shaded area that you're going to revolve, okay? All right, so let's do that now. Put that calculator away.
That around an axis,
Put the calculator
that
away.
can give us a different kind of solid.
Okay. Huh? Yeah. Okay, so do you see what happens here? That yellow area, when you rotate, you now have an empty space in the middle, right? That's what we're going to do today.
Whose cross-sections are not circles, but rather things called washers. A washer is like a ring, and it will have two radii, the one from the axis of rotation to where the solid starts, which we call the inner radius, and one from the axis of rotation to where the solid ends, or the outer radius. Just like the circle in the previous example, whose radius changes as it moves through the solid, this washer will also change as it moves through the solid, and both the inner and outer radii change according to these two functions. Let's take the functions y equals x squared and y equals x.
Just see the animation again.
Area here between x equals 0 and 1 that we can imagine is filled in. We already learned how to calculate this area by integration, but now let's rotate.
You see how that looks? And then you've got that like space in the middle. Okay?
That will give us this.
All right. So if we move on then, right, as you saw, if you have, two functions, then when you rotate or when that is revolved around one of the axes, you've got a little empty space here in the middle when you take a cross section. All right. So for example, if this is your y-axis and this is your x-axis, and suppose you've got, one function here, and then you've got another function here. So we'll call this f of x, and we'll call this g of x. It's this area that you are now going to, revolve around this. Okay? So what happens? That shaded area, comes out here and then goes back in, but that space here, that empty space here, leaves an opening like this one here. Okay? So imagine only the purple shaded part is being rotated, right? It comes out like this and in like that. And this middle part is just empty space. Okay. Now, what we wanted to do, right? So imagine the disc looks like this, or the washer rather. So you've got this one here that turns like this. And then you've got g of x that turns like this, and inside here you've just got empty space. So now, what are these radii? What's the radius? Remember, this is a circle. So what I want to do is, how do I find the area of the shaded circle here? Well, yeah, I have a big radius and a little radius, right? So I'm going to do pi r squared minus pi little r squared. Okay? And what are these big and little radii? The big radius goes from the axis to the upper curve, that's big R. And the little radius goes from the axis to the small radius. Okay? The lower function. Okay, questions? Okay. So now, if this is A, can I factor out a pi? I can. Right, and then I just get big R squared minus little r squared. And if that's the area and I wanted to integrate the area, then what I get is what it looks like here. Okay, so volume is pi big R squared minus little r squared. So big R is the outside function, little r is the inside function. Yeah.
So in this case, it'd be like for other words, if we're looking at it not in the version, outside would be the upper one.
Yes, exactly. So that's what I say here. Big R is always the curve furthest away from the axis of rotation. Okay, so we're rotating around the x-axis. I've got one curve here and one curve here. Which one is farther? It's f of x. So that's the big R. Which one is closer? G of x. That's the little r. Okay? And little r is always the one that's closer to the axis of revolution. Okay, so why don't we put that to use here? The region in the first quadrant enclosed by the y-axis and the graphs of y equals cosine and sine is revolved around the x-axis. Here, okay, so that's the y-axis, that's easy. But now I'm supposed to have sine x and cosine x here. And which one is which? The upper one, is that sine x or cosine x? Cosine x. And this is y equals sine x. And this y-axis. So it's the region defined by those three curves. And now I want to take that and revolve it around here. Okay, so look, if I were to trace out the sine x, that looks like this. If I were to trace out the cosine x, that looks like this. And now I took that and I revolved it around here, and it looks like this. Okay? And that space in the middle, that disk in the middle is empty. So what I want to do is this. How much is the big radius here? How much is the big radius? Well, the big radius, big R, is the distance from the x-axis to the curve that's farthest away. So it's cosine x. Little r is sine x. It's this one. It's always, the radius, remember, is always the distance from the axis to the curve. Okay? So, from the axis to the curve that's farthest away, that's big R. From the axis to the curve that's closer, that's little r. Only because that one's farther, so it's a bigger radius. It's a bigger distance. So now what I want to do is, for volume, I want to say, okay, pi big R squared cosine of x squared minus little r squared dx. And now I want this to go from 0 to some value, right? Okay, so where is this? What is this value? Without our calculators, do we even know? Where is cosine x and sine x the same? Pi over 4. Only for pi over 4 is sine of x and cosine of x the same. What's sine of pi over 4? Root 2 over 2. What's cosine of pi over 4? Root 2 over 2. So that's pi over 4. So now this is 0 to pi over 4. Okay? Now, if you have your calculator with you, can you also use that to find this one? Of course you can, but look at how much time it saves us, right? If I know, oh yeah, cosine and sine are the same at pi over 4, as opposed to graph cosine, graph sine, second calc, intersect, upper bound, lower bound, guess, sure, whatever. Oh, it's this. Now let me store this. Now, like, so much extra time, okay? All right, so now we're going to go and plug this in. And I want everybody to plug this in right now because it gets tricky with the squares of the sine and cosine functions. So don't forget the pi, and then we do get here 1.571 for the volume here. Okay? All right, let's do another one.
So it's always the same setup though. It's pi r squared minus or
If you were to do
what are
like
these types of problems though? Like what name did you give it?
Well, it's it's the washer method, but I won't tell you use the washer method. You should know that when you're looking for volume of a solid generated by two curves, this is what you're doing. By one curve, it was just pi r squared. Yeah.
You always give us like the mirrored.
I don't. I will not. Like, look at example 5 right now. I've given you nothing. You have to do it all. So let's do it all. Find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So on the one hand, I have y equals 2x. So that looks like this. Here. So that's y equals 2x. And then I have the line y equals x. And then I have the line x equals 1. That's this. So highlight the region that's bounded by all of these. It's this. Correct? Now that's the region that's going to be revolved around the x-axis. And when you revolve that around the x-axis, let's just see what it looks like. So this is the red one that gets reflected. That's the purple one that gets reflected. So basically it's that region that you now revolved around. Do you see that? Now, you really don't have to do this, fancy schmancy, like rotating and revolving or whatever. Even if you just have the stuff on top, now you're revolving around the x-axis. So you say, okay, x-axis and up. What's the curve that's farthest away? Y equals 2x, right? So that's your big R, y equals 2x. What's the curve that's closer? That's little r, y equals x. And now when you have two functions, your volume is pi r squared minus r squared. Okay? Dx. So the volume is going to be pi 2x quantity squared minus x squared dx. And now, these bounds here, are they going to be values of x or y? I'm yelling because I'm excited, but is it going to be values of x or y? X, because it's x dx, x. So, this goes from x equals 0 to 1. Okay? Now, you know what? It's actually quicker if we do this by hand. Because, what do you get here?
The 0 goes away.
Yeah, the 0 goes away, and then you get 2x cubed over 3 minus x cubed over 3. Huh? Yeah. Okay, so look, how much is this? This is 4x squared minus x squared, is that right? So you're really integrating 0 to 1 times pi 3x squared. Am I right? Am I right what I did there? Because it's 4x squared minus x squared. I just did algebra, right? So then when you integrate, it's pi x cubed, because it's from 0 to 1. So that's just pi. Yeah? Okay. Is this 4x squared? Is this 4x squared? Minus x squared, is that 3x squared? Yeah? No calculus, just algebra 1. When you integrate that, 3x cubed over 3 is x cubed. From 0 to 1, that's just pi. You could do that, of course. Whatever saves you time. Okay. Oh, this was supposed to be example 6. Because now we're going to move on to example 7. The region bounded by y equals root x and y equals half x. And for part A, it says find the volume generated by revolving this about the y-axis. So first of all, where is y equal? This is y equals root x, right? And then this is y equals 1/2 x. Okay? So let's take a look at where these two meet, right? So it's the point where root x is equal to half x squared, right? And now if I square both sides, x is 1/4 x squared. Oh, it's 1/2 x. And then I squared it. So now if I multiply both sides by 4, 4x is x squared. And now x squared minus 4x is equal to 0. Factor out an x. X is 0. X is 4. So this point here, x is 0, and how much is y? You can plug it into any of them. Y is 0. This point, x is 4, and how much is y? You can plug it into any of them. Y is 2. Okay? There you have it. Right, but if you weren't given anything, yeah. So now it's this region that I'm revolving here. And so what it's going to look like is something like this and that, right? That's what it's going to look like with an empty space in the middle. Yes?
You're going to, for the test or quiz, do you want us to draw out what the reflection would look like, or you're just doing it?
No, you don't have to draw the reflection. At least draw the graph, like the actual functions, yeah. But you don't have to draw the reflection. Okay, so now, how much is big R? Again, I'm revolving this around the x-axis. You're revolving around the x-axis. So you go, okay, x-axis to graph, right? X-axis to farthest graph is how much? Root x. X-axis to closer one is 1/2 x. So volume is pi big R squared minus little r squared from 0 to 4. From x is 0 to x is 4 dx. Remember, x dx, x equals a, x equals b. Okay, you got to be consistent. We put this in the calculator, and remember the pi there, and so that's going to turn out to be 8.378. Okay? Now, when I go to put this in the calculator, I don't do the square root of x squared. I just type in x, and I type in 1/4 x squared. You know what? Better yet, I would type in, if I was plugging this into the calculator, I would type this in as x minus, what's 1/4? 0.25 x to the 4. That eliminates the parentheses around the 1/4. It eliminates the, the x squared to the square to the right? Okay. Any questions here? Okay, now it says find the volume of the solid generated by revolving the region about the y-axis. So now I want to revolve around the y-axis. Okay? That means this region is going to get revolved around here, and it's going to look like this right here. Okay? So now that it's around the y-axis, things are going to be different. Now when it's on the y-axis, it's got to be y, dy, y equals b to, c to d. So what we have to do is solve everything in terms of y. That means if y was root x, then what's x equal to? Y squared. Okay, so that's my one function. And then when y equals half x, what's x equal to? 2y. So these are the ones I'm going to use now. Okay. If I'm revolving around the y-axis, then for my radii, I have to go axis to graph. Axis to graph. So what's the big R? From axis to the graph that's farthest, 2y. You see how it's consistent? And then little r is from axis to the graph that's closest, y squared. Questions? Yes.
So it's from the y-axis still to the function to the right.
It's always from the axis of revolution to farthest graph, axis of revolution to closest graph. Okay? All right, so now my volume, it's going to be y dy. So big R, 2y squared minus little r squared dy, yes, pi here, thank you. And now we're going to go from 0 to 2, right? From 0 to y equals 2. Because remember, this was x is 4, y is 2. I got to go to the y value now. Okay, so y dy. Will you get the same answer when you do this?
Yes.
No, because you get a different shape, right? Here, you're getting this shape, right? That's what it looks like. Here, you're getting this shape. That's what it looks like. You see how, like, it's a different cone, okay? What's the answer here? 13.404. Okay. 13.404. Now, this one here, I'm actually not going to do this. We're just going to skip it forever, for good.
Forever?
Forever.
Cross it out.
Cross it out.